ひど。なんだこの操作性は。何時からだっけ。17時30分にしようかな。じゃあ17時30分にしました。もう一回で、ブルーキャットで、編集で、ここ17時30分で、18時30分こんな感じかな。良いですか。良いです。それでコンパス、これも、17時30分、それで15で、これで放送、これでいけるかな。それでWalk Irish Country Mile、で、あれ、変なのブルーキャットの方からいくと、ここにテキスト PDF がありますと。それで、これダウンロードできますと。で、開いて、OK ね。これは消していいや。それ大体30ページ。大体30ページに行けば、こうです。ジュールヒーティングが終わったので、トムソンエフェクトからいきます。Problem number 3, Thomson effect. Suppose that in addition to the applied electric field in problem 2, there is also a uniform temperature gradient, nabla T, in the metal. Since an electron emerges from a collision at an energy determined by the local temperature, the energy lost in collisions will depend on how far down the temperature gradient the electron travels between collisions, as well as on how much energy it has gained from the electric field. Consequently, the power lost will contain a term proportional to E dot nabla T, which is easily isolated from other terms since it is the only term in the second order energy loss that changes sign when the sign of E is reversed. This is the only term in the second order energy loss that changes sign when the sign of E is reversed. So that this contribution is given in the Drude model by a term of order Ne tau over M d how do you call it? Decorated E divided by dt E dot nabla T gradient T, where decorated E is the mean thermal energy per electron. Calculate the energy lost by a typical electron colliding at R, which made its last collision at R minus D. Assuming a fixed, that is energy-dependent relaxation time, energy-independent relaxation time tau, D can be found to linear order in the field and temperature gradient by simple kinematic argument, which is enough to give the energy loss to second order. So complicated. Suppose that in addition to apply electric field in problem 2, there is also a uniform temperature gradient delta T in the metal. Shall we check the solution first? Okay, so let's see the solution. There's an Ashcroft-Mermin solution. Let's see this one. Assume a collision at R1, a next collision at R2. The change in energy is this. The last term is simple Joule heating. There is still average in the first part, since we have to find the difference in position. We have to find the difference in position. The first term gives a contribution. Delta E average delta epsilon average is dE dt. T average where we assume that the temperature gradients are small and can take the derivative at the average temperature of the sample. We have R2 minus R1 is V1T minus okay, and hence the average delta T average energy loss per collision. The power loss it's complicated. Very complicated, but I think one can follow this argument. Let's see the question. Which is easy isolated, the power lost will contain a term proportional to E dot. Very interesting. So that this contribution is given in Drude model by a term of order this. Let me see. Okay, let me turn on my light in my room. Okay, it's okay. E dot decorated E is the mean thermal energy per electron. Hey, how do you get mean thermal energy? I think question is how we get this done. Okay, so this is more like we don't have e square. Hey, is this e square or e? Interesting. So this is conductivity divided by e. Sorry. Okay, this one is conductivity divided by e, right? So, and this is a voltage divided by sample size, and this is temperature gradient. We just measure temperature of this position and this position. So this is temperature 1, this is temperature 2, then this is this is temperature gradient is T2 minus T1 divided by L, assuming this is L. Okay, but the question is, how do we get this one? How do we get this one? So that this contribution is given consequently the power lost will contain a term proportional to something which is easily isolated from other terms since it is the only term in the second order energy loss. What do you mean by second order energy loss? That changes sign when the sign of E reversed. So that this contribution is given by the Drude model by a term of order something, where decorated E is the mean thermal energy per electron. Calculate the energy lost by a typical electron colliding at R, which calculate the energy lost by a typical electron colliding at R, which made its last collision at R minus D, assuming a fixed, that is energy dependent, relaxation time tau D can be found to linear order in the field, and temperature gradient in the field and temperature gradient by simple kinematic argument, which is enough to keep the energy, which is enough to give the energy loss to second order. I'm not quite sure what does he mean by second order. Second order. Okay, so I think I would just skip this one because this is no, I don't know. Okay, maybe I can explain a little bit. This is like the power. Okay, so this power, you can. I hope I can write. So if you have sample, for simplicity, we just assume two terminal, two electrode measurement, or two probe measurement. Then one side of the sample, the temperature of the one side of sample is T1, and the temperature of the other side is T2. Okay, then we can also assume the length of the sample is L. Then we assume one side of the sample, the voltage is V1, and the other side is V2. Okay, so then we assume there is a electric. Okay, for example, we see one side, one way. It's a little bit complicated, right? We can pass current. Okay, first we can consider passing electric current in this way. Okay, so which we call IR, and second we consider passing electron in this way, IL. Okay, then we see the voltage difference. This is just IR. Magnitude of I are same. IR equal IL equal I. Okay, let's assume this way. So then here we find voltage difference. Yeah, voltage difference is something like this. Let me see. Sorry. V1, V2 minus V1 of minus 1 and I don't have space. Let me do this way. V2 minus V1, where we pass a current in this way, is different from the V2 minus V1, where we pass a current in this way. This value is different. Then we take the whole absolute value again. So this value we can call the delta V1, 2. Okay, so this is like a directionally dependent resistance, one can say, and that direction is given by delta T. Okay, so this is called delta V. Then let me see, J, comma, it's complicated. Okay, so this is delta V, then I think I have to make this half. So actually this one I have to multiply 1/2. Okay, so I define delta V1, 2 this way. Then delta V1, 2 times I is just given. This is the P. This is the P above times the volume of the sample. Times temperature gradient. Yeah, I think so. T2 minus T1. Yeah. So then we can insert this P value. P is this this guy. So I can maybe delete this above. We put this P into this here. I hope this helps. Does it help? Let me see. Okay. I think this is okay. So this is some measurable quantity. Yeah. This measurable quantity is I think this is wrong. I think I am wrong. So this measurable quantity is something like this. D epsilon dt. I ignore this one. Then this thing is like a T2 minus T1 divided by L. Then times E to J times volume. Yeah. Okay, volume, we can rewrite volume. Volume is A times L. And this is current. Okay, this is current. This is I. And we can cancel LL. Okay, then we can cancel I, this side and this side. Then, okay, so then we obtain substitute. Delta V12 divided by T2 minus T1. This is experimental quantity. We can obtain this value experimentally. This is equal to 1 over E d epsilon dt. So this is a useful result, I think. This is electron energy the increment of electron energy divided by increment of temperature on average is this. T2 minus T1 E delta V12. So this means this theoretically or fundamentally theoretically useful information can be obtained from experiment. If you make this kind of experiment, you can obtain this left-hand side useful information. Yeah, I think that's the core message of this program. Number 4. Oops. Anyway, okay. So I will try to do next program next time. Okay, see you.